Hi class, this is Dr. E again with a review of Chapter 7. As you can see that Chapter 7, you're not assigned the whole chapter, just portions of it, so we'll go over those portions. Before we start, let's do a quick review about the parts of the long bone in order to talk about how long bones grow. So we have the main shaft of the bone, and that is known as the diaphysis. We also have the two ends. So there's a proximal epiphysis and a distal epiphysis, and then that portion in between that is known as the metaphysis. The metaphysis, that is used to be where the growth plate was, or the epiphyseal plate, made out of cartilage, and then it ossifies in order to make bone. And that's what we're going to be talking about, the growth of at the epiphyseal plate, which again is the replacement of that cartilage with bone tissue, a process known as ossification. So that cartilage cell, that plate, is made really out of 4 layers. When you look under a microscope, you're going to find 4 layers. So I'm going to just go to the pictures to kind of take a look at these layers. The very first, this is the part of the bone that we're looking at. So we're kind of going over the layers from top to bottom in this picture, or from superficial to deep. So the very first layer of cartilage is known as the zone of resting cartilage. And that is really pretty much anchoring that epiphyseal cartilage to the epiphysis on top. It's made just like the name indicates. It's made out of cartilage cells that are in resting phase. The second zone, or the zone that is a little bit deeper to it, is known as zone of proliferating cartilage. And now you can see that these cartilage cells are undergoing mitosis. The third cell is known as zone of hypertrophic cartilage. You can see that the cartilage cells are bigger in size. They are growing, and they are starting to become calcified. They are getting older in age. So these cartilage cells, as they age, they are becoming calcified and getting older. Then the fourth stage, or the fourth zone, that's the zone of calcified cartilage. These cartilage cells are pretty much dead at that point. They have been fully ossified or fully calcified, and then the osteocytes are going to come in, and so we've now replaced those cartilage cells with bone tissue. There should be here a slide that shows a mnemonic for cartilage cells. So I'm going to show it in this view. For whatever reason, it's not showing when I put it in slideshow. So for the mnemonic for the layers of the epiphyseal plate, our real people have careers. So R is the resting zone, P is the proliferative zone, H is the hypertrophic zone, and C is the calcified, or the zone of calcified cartilage. Now let me go back to the slideshow. So the growth at the epiphyseal plate happens through the interaction between different cells. As we guys might remember from AP1, osteocytes are the mature bone cells. We also have osteoclasts and osteoblasts. Osteoclasts are breakdown tissue, or breakdown bone tissue, so that will lead to the release of calcium the bone will lose the calcium, and that calcium will be released into the bloodstream. While osteoblasts does the opposite. Osteoblasts are really considered baby osteocytes. They calcify bone, so osteoblasts, when activated, will take the bone from the bloodstream and deposit that bone will take the calcium from the bloodstream, deposit that calcium onto the bone, and hence making bone tissue. When ossification is complete, that means that all of that cartilage, all of the growth plate has been replaced with bone tissue, and at that point, bone growth is not possible. As the bones grow, the bone tissue, if bone grows after that point, and we'll see this would not be normal physiology, growth in length is not going to be established, but growth in width would happen where bone tissue is now deposited under the periosteum. And you'll take a look in the next couple of slides how that can happen as a pathology. For homeostasis of bone tissue, homeostasis again means maintaining a balance. And in order to maintain a balance of bone tissue, that means that we are removing dead cells and replacing it with healthier cells or fresh, new, young cells. So we usually tend to think of bone as dead tissue, but bone is definitely a living tissue where some of the bone cells or osteocytes become old. We have to replace them with newer cells. And that process is known as bone remodeling. It occurs throughout our whole life, and it is made out of bone resorption followed by bone deposition. So bone resorption is the removal of the older bone cells, and that is the function of the osteoclasts. While bone deposition would be depositing or making fresh new osteocytes, and that is the function of osteoblasts. As you can see here, about 10 to 20% of our skeleton is replaced each year. As we age, though, bone resorption is going to be much faster than bone deposition, and that will lead to osteoporosis. Some of the factors that affect bone growth. We have 3 vitamins, 4 hormones, and physical stress. So for the 3 vitamins that we talk about, we've got vitamin D. As we all know, vitamin D is important for calcium absorption. If you don't get enough calcium, that could lead to rickets in kids or osteomalacia in adults. I'm going to go to the next slide to just show you a picture of rickets. So rickets here, you can see the rosary beads on the ribs. That's what it's called, on the chest. And then you can also see the bowing of the legs in kids with rickets. Osteomalacia means softening of the bone tissue because you no longer have enough calcium in the bone, so the bone is thought of being softer than it should be. It's not as hard as it should be. Vitamin A is important for the activity of both the osteoblasts and osteoclasts. So if we're deficient in vitamin A, that can lead to bone development retardation. Vitamin C is important for collagen synthesis, so anything that has collagen in it would be definitely affected. So your bones are going to be slender and fragile. Skin will also be affected, so if you can think of anything that has collagen in it, the deficiency of vitamin C will lead to a defect in that structure. Moving on to the hormones, so growth hormone, as you would anticipate and expect, would stimulate cartilage cells. If somebody isn't getting enough, doesn't have enough growth hormone, so there's an insufficiency of growth hormone in a kid, that will lead to what is known as pituitary dwarfism. So growth hormone is released by the pituitary gland, as you should know from chapter 13. So if there isn't enough growth hormone coming out of the pituitary, that will lead to pituitary dwarfism. Excess amount of growth hormone, though, can lead to 2 different conditions depending on the age of the patient. So if it happens in a child where their epiphyseal plates have not ossified yet, that would lead to gigantism. If it happens in an adult, that would lead to acromegaly. So remember, in adults, all of the epiphyseal plates have been replaced by bone. So the bone can no longer elongate, it can no longer become longer, but it would become wider. And that's what we were talking about when we mentioned that bone can thicken because of the deposition underneath the periosteum. That is the pathology that I was talking about. So I'm going to take you to a slide where you can see the difference between gigantism and acromegaly. So this is the normal person. This individual had an increase of growth hormone before puberty, so you can see that the person is much longer. Everything really is disproportionate, so the lower limbs are longer, the upper limbs are much longer. In contrast that with this young lady down here that got an increase of growth hormone after puberty, so after the epiphyseal plates have been ossified, she had a very normal features, but now because of the bone being unable to get bigger in length, now the bone is growing where it's getting wider. So you can see that the facial features have changed as time goes by, facial features have totally changed where she's most, maybe unrecognizable. And then if you look at the arms as well, you could see that they are disfigured, or the hands. As for thyroid hormone, the thyroid hormone is important for osteoblastic activity, so it helps in the replacement of cartilage with bone. Parathyroid hormone, that will stimulate the osteoclast, so it will really break down bone and release again that calcium from the bone into the bloodstream. Sex hormones, so estrogen and testosterone, depending on the gender, that really promotes bone growth. So as we all know, there's always that growth spurt that happens, during puberty, and that is because of that spike in the sex hormones that will lead to that, huge, or that fast growth spurt that happens during that period of time. Last but not least is physical stress. So when we think about, physical stress does not mean stressed out because of exams. Physical stress pretty much means exercise. So the body is moving. The lack of movement will lead to resorption of bone tissue. So we are losing bone tissue if we're not moving. As we move, that leads to healthy bone remodeling. And that is why we always ask seniors to always be moving, because that physical stress is always it will stimulate their bone formation. So we've seen these images here. Now we're going to be talking about the hormonal control of blood calcium, or the homeostasis of calcium levels of blood. So just like anything else, we want to keep it within normal range. But if the blood levels are too high, that is a condition known as hypercalcemia. There is a process the body does in order to bring back to lower the calcium levels back to normal. Know the following, though, that calcium keeps on going back and forth between bone and blood. So if it is released from the bone tissue, it is going to be released into the bloodstream. And the opposite is true as well. So if we take calcium from the bloodstream, we can deposit it onto bone. So that is kind of like where calcium goes back and forth in this whole process. So in the condition of hypercalcemia, that stimulus will stimulate the receptors of the thyroid gland. The thyroid gland is going to release calcitonin. Calcitonin then will activate the osteoblasts and deposit that calcium, all of that calcium that is too much in the bloodstream, it will deposit it onto the bone. And that will bring back the blood calcium levels back to normal. So calcitonin tones down the blood levels of calcium. Its name is telling you what it does. While if the blood levels of calcium was too low, and that is a condition known as hypocalcemia, that stimulus will stimulate the receptors of the parathyroid gland. The parathyroid gland will release parathyroid hormone. That parathyroid hormone will reach the bone and activate the osteoclasts. Osteoclasts are going to basically break down the bone tissue and release any calcium found in the bone into the bloodstream. And that will bring the blood calcium levels back to normal. And that concludes Chapter 7.